Good afternoon, all. I hope I am audible. So today we will focus more on data types, nets, registers, vectors, and integer and real things. Okay. So as I mentioned in that yesterday's sessions, that verilog uses different data types to represent the signal stored elements and simulation variables. So choosing the correct data type is important, whether it is a synthesizable hardware design, simulation correctness, timing modeling, test bench development. So you have to choose the correct data type. So the common data types are nets, registers, vectors, integer, real, and time. These all are the common data types which we will be using it. So today our session is focusing on these things. Okay. So in a broad category, you can differentiate or you can categorize the uh, verilog data types into net data type and variable data type. Okay. So in the net data type, it is nothing but a physical connection. It represents the physical connection. That is where net data types. So for example, wire, you can use it as a data type, and then you can assign a variable to that. I mean, and using that identifier, you can go and use it for any um, logical architecture. Then the try W and W are wire and combined, wire and R combined, and supply 0 is ground and supply 1 is VCC power supply. Okay, so these are the things they are using it. And the other category of the variable data types are store values until changed. So it is something like it can store the value. This cannot store the value. This will store the value. Okay, this will store the value. And example register, reg, integer, real and time. It is not synthesizable. Okay, so real, time, integer, and reg are variable data types. So first we will try to look into the focus on the net data types. So the net data types, it represents the connection between the hardware elements. So something like a wire, okay, it cannot store the value. Okay, so it represents the interconnection. It does not store value by itself and must be continuously driven. So models physical wiring. You can think of an electrical connection. Okay, so that is what this net data types looks. So wire Y and Y A and B. So this is the logical things we are using it, and the wire, it is one of the example. Okay, just so in that particularly wire. So in the net data types, mostly we will use wire. Okay, mostly we will use wire data type, and then it is used for the combinational connections and the modules for which we want to do the interconnect, which you want to go and do the interconnect. Then the continuous assignment. So for all these things, we'll go for this wire. So this is the assignment, continuous assignment. This is continuous. Okay. So it's a combinational XR. So we will use the wire. This A and B can be the input, output, such kind of things. Characteristics. It cannot store value. Driven by assign. Module output. It is driven by assign only. And it is synthesizable, where you can synthesize as like for the real hardware. The next data type is tri tri-state net. Actually, wire also will go for tri-state net. For historical purpose, they kept this tri. So mostly, if wire and tri will work same, but for historical reason, they kept it this tri also. Okay. So it is used. The thing is, keyword is tri, and the database. Okay, it will allows multiple drivers, shared buses, bidirectional interfaces. Okay. If this is not actively driven, it is high impedance. The if we are not driving it, then it is having an high impedance. Is that now wired plus and W is W and okay. So W and IRQ line. Okay, so we have driver 1 and driver 2, and driver 1 is 1, driver 2 is 0. Okay, so when driver 1 and driver 2 1 and 0, what will be the output? It will go and of these things. Okay, that is what this W and. So in rare case, in the rare we will use it in the RTL. Okay, so this is W and the same for WR, wired R. So when the multiple drivers are allowed, so resolution uses the logical R. So here it takes the R of these two drivers and put it over there. Okay, this is what about the wired R. Then supply 0 is high, and supply 0 is ground, and supply 1 is VDD. So it's a constant power signal. So mostly in modeling we will using. So most modeling use. Okay, it represents logic I and logic 0. So till now we looked into the net data types. Okay, now we will see the register data types. Okay, register data type. Despite the name, reg does not always mean hardware register. It means variable that can hold value until reassigned. Okay. So it is used in, it is not in the structure, I mean, not in the assigned continuous thing. It is used in the procedural blocks. That is always block and initial blocks. Okay. So if you want to use, okay, reg q, if you use reg q and if you give assign q, then it won't work. Then it gives an error. So whenever you try to use reg, and if you want to use that variable, you have to use it in the always block or initial blocks. Okay. So always at, that is the thing, and inside. Okay. So for combinational, you will give the wildcard star. That means it takes all the inputs and outputs as a sensitivity list. But here we are in the sequential, we have to give the clock edge. That is the sensitivity. So the parameter passing in the bracket of the always block, that is the sensitivity list. Sensitivity list. Okay, and this is also for the combinational procedure lock also. So when you give the combinational thing, we will take actually we can give a, b and all, but usually sometimes we might be forgetting the input. So if we give odd this wild card, it will take all the signals. Okay, all the ports, sorry, all the ports. So when it comes to the future, the wire cannot store the value, reg can store. It is driven by assign module outputs, procedural blocks, that is the initial block or always block. Assigned, yes, assign you cannot use the reg block. Always block assignment, we cannot use wire, but we can use this reg block. Okay, and both are synthesizable. These both all are synthesizable. Now we will try to understand the scalar and the vector. A signal can be scalar, that means only one bit. Vector is multiple bits. Okay, so scalar simply clock, it is a one bit, one high, low, likewise only it can do these things. Vector, a data of 8 bits. Okay, so this is vector and this is scalar. So easy, but a small things you have to keep in the mind. So when it comes to the bigger part, you might not lose the control. So vector represents buses or multi-bit signals. For example, what type and how much bit, first MSB, then LSB. LSB will always 0. So MSB means if it is 8 bit means MSB will be 7. So 8 minus 1, it will start with that. Okay. Then the name. Okay. So now this data is a vector, count is a vector because it is having a multi-bit. Okay, because it is having a multi-bit. Next comes the indexing. Okay, access individual bits. Okay, for example, data of 3, bit 3 selected. This is where accessing the individual bits. Slicing, so accessing not all bits, any bits from one order. For example, the upper 4 bit you have to access, we can use something, the slicing operator, colon 7 to 4. Okay, it will extract the upper nibble. So it helps us in the bus manipulation, field extraction, and the protocol parsing. In all these things, these slicing will be used. Then packed representation. So vectors are packed with the bit collections. You see that it is packed with the bit collections. So some instructions you want to implement, you want to go and implement an instruction which is of 32-bit size. You can go and use. So it is of packed. Okay. So this is used in processor, buses, and registers. So next, integer data type. Okay, reg. Okay, it is unsigned. Default is unsigned. You can make it signed also by giving the things. But here integer, it is a 32-bit. The size is 32-bit and it is signed variable. Okay. So how are we going to assign a thing for this syntax? Integer count. So it is a signed simulation variable, arithmetic operations. For example, in the for loop, you can go and use this I and you can change the things. Okay. So commonly used in the loop counters, test bench variables, and simulation arithmetic. So these are the common things we go and use it. So when it comes to the synthesizability of integer, it can be synthesizable in limited cases. For loop counter, it is okay. But for the hardware data path, you try to avoid integer, you go for the registers. Okay. So that is what it is recommended. It is not like that you cannot use it, but it is recommended to use reg data types. Then if you need a floating point, you can use a real, but it is not synthesizable. Maybe only for simulation purpose you can go and use it, but it is not synthesizable. So floating point numeric type, okay, real voltage, okay, example, real pi 3.145. So floating point, simulation only, it is not synthesizable. You have to keep that in your mind. So for analog modeling, test bench calculations, and timing computations, you can go and use. So we can use it only for the simulations and not for the synthesizable. If you want to make it in for the hardware synthesizable, no, we cannot use real. Then time is also the same. It stores simulation of the time. So you can use the time keyword and a T1 and the start time, and the start time you can, and if you can access the current time by using the dollar and the time variable. Using that, you can go and access the current time. So simulation timing experiment, you can go and use this time. So this is the same as this. Okay. So signed declaration, whatever the thing default you do apart from integer, reg and all, it is unsigned. So if you want to make reg for the signed, you have to mention its sign value. So signed, so reg signed, so it is a signed 8-bit. It is a signed 8-bit. If it is a signed 8-bit, if the 8 bits all are 1, then that means it is -1. And if it is a signed 8-bit, and if you give representation all are 1, then it is 255. So that is the difference. So when we try to use these type of keywords, the default is unsigned. But if you need a signed value to store or something like that, so you want to give the signed. Okay, and then these things you have to use. And this is the an example. If you make all 8-bit 1, the most significant bit will be for the representation of the sign, so minus, then this. Okay, we want to take it as a 2's complement. So 2's complement means all will become 0. If we add 1 negative and then 1, so it will become all 0 plus 1 1. And since because of this it is -1, so it becomes -1. And for the unsigned, the MSB is not for the sign, the total is used for the value, so you will get 255. So we want to be careful with these things. Okay, next, memory arrays. This also we will see by tomorrow, but I am trying to introduce it now itself. Memory arrays, it is array of registers. Okay, so try to understand array. See, whatever the thing right now we put, that is vector. Okay, so, and if you try to put this, it becomes array. So a memory is having a size, yesterday itself I told, okay, from 0 to 255, so 256 is of size, and each is having an 8-bit. That is what it's meaning. Each is having an 8-bit. So it is having 256 location, and for each location they have 8 bits are each. So you can use these kind of things in the RAM modeling, ROM, and lookup tables. So these memory arrays will be useful for that. Okay. So for example, the RTL usage for the combinational, already we did, but I am trying to explain what is happening there. Okay. So A and B is a wire. So it cannot store value. So it is driven. It is continuously something it want to drive. Okay. and output also y, and we are assigning y equal to, this is the logic architecture we are giving to the gate. Okay, so this is the meaning. So when you use wire, you can use only the assign keyword. Try to understand it. Suppose if you use reg, you cannot use assign. You have to use always block or initial block. Okay, so since it's a sequential, we want to mention the clock edge. Post means positive clock edge. This is the positive clock edge, and this is the negative clock edge. So neg edge, neg, positive edge, and you have to represent the clock. Then it is an non-blocking assignment, less than or equal to. So always for the sequential, we will giving the non-blocking assignment, and for the combinational, usually we will be giving the blocking assignment. Okay, so maybe in later classes, I will talk about this blocking and non-blocking. For a time being, you try to get these things, wire and reg. So when it's a continuous, this you have to use procedure block. This is something you have to go and use the continuous or assign block. Okay, suppose bus, for the bus you don't want to store the data because it want to go and deliver the things. So it is a 32 bit size bus, but the counter, it want to store some value, so you use registers. Okay, and for the loop variable, go and use integer I, no problem. Okay, and for simulating something a max, so you go for a real and temp. It is not synthesizable. For calculation temporary, you can go and use for the math operations. So these are some RTL usages where you can go and use and work on it. Okay, but this you cannot synthesize, maybe only for simulation, but others can synthesize. You can use it for the synthesize. So what are the mistake we will go and do? No, when we try to use wire, we will go for always combinational block, and then we will try to use. No, when it is an wire, you have to use assign only. You have to use assign when it comes to the wire. Okay, so wire cannot be procedurally assigned. Try to make a note of it. Okay, using reg with assign, opposite. Okay, we will create a variable with the reg data type, and we will use assign. Okay, so that is what the one thing. Okay, then another thing what we will use, no, using integer for hardware bus. So integer data hardware, it is a integer is 32 bit. We will think it is a 32 bit, but it is a bad usage they are telling. They are asking us to prefer this kind of things. It works, but somehow they are telling that go on to use this reg, like these kind of things. Okay, next we will be forgetting the signed arithmetic, so it will cause incorrect comparison and max. Okay, so these all are some pitfalls where they a newly thing if you go and write the code. Okay, so that is one thing which we want to take care. So for the wire, suppose if it is a combinational interconnect, go and use wire, and for the procedure variable, go and use reg. For buses and registers, go and use vectors. Okay, and for the test benches, use integer real time because it is only a test bench code. Okay, so unnecessarily exhaustive net types and real in synthesizable RTL, integer for data path. So these things they are asking us to don't go and use such kind of things. Maybe the right now in the modern the system verilog, okay, instead of reg wire they are using logic. Okay, so it is cleaner and less confusing, but classical verilog understanding remains essential. we want to understand the classic verilog, even though the system verilog makes it easy, it uses logic, but they are telling that understanding the classical verilog understanding, it is very much essential for us. Okay, so we have a wire, try, w and wr, reg, vector, integer, real, time and memory array. We lent and looked into it. And if it come to the synthesizable, wire is synthesizable, tri-state is limited. So if you want to use, don't use these things, they will be using wire. Okay, these things are rarely we use. Okay, and register is an synthesizable, vector multi-bit signal, that is also synthesizable. So integer, you go and use limited sticks, don't use full. Then these two are not synthesizable, real and time, it is only for the simulation. Memory array, as I mentioned in the one of the example, RAM or ROM modeling, and it is synthesizable, where we will use wire or reg for making the memory array. Since it's a memory, we want to store the data, go for the reg. Okay, so these all are some concluding points about the data types till now, what we have been looked into it. Okay, so in summary, if we want to use net, go for physical connection and wire most connection. For register, procedural storage variables. Vectors use buses and multi-bit. If you have buses and multi-bit signals, go for vectors. Integers, signed arithmetic variables. Floating point for simulation only. Okay, so these all are essential foundation for writing a correct RTL code. Okay, so the same data types, I am repeating it again from the yesterday slide. I went and put it over there. So you have to understand this unknown and z state. Okay, so net, this try supply, and we went and looked into it. This is the procedural. Okay, so vector bits, both wire and reg types can be declared as a multiple bits. Okay, multiple buses. So arrays can create memories or arrays of registers, that you know. Okay, so these all are something about the today's theory part. Okay, and let us try to move into our practical things. Whatever we learned for the thing, we will try to understand it by the coding. Okay, we will try to understand the things by coding. Maybe it might be the basics, but still revisiting the basics is good. Okay, so always try to revisit the basics and try to get an idea. That is very much important. Okay, so now let me go and open the data types. Okay, I have kept some many examples for it. Okay, so let me go and open the things. Okay, maybe I might be opening it in the wired. Okay, and then test bench. So let me take it this, it will be a good idea. Then let me take the open the terminal, and let me bring the terminal also here. Okay, so let me put it like this, and then let me put it like this, so that you will be having an exact view of what is this, and at the same time I can go on compile and show you the stuffs. Okay, so that it will be easy for you guys to view it. Okay, so now I'm showing a simple example. Okay, simple example of demonstration of a wire data type. Okay, so now wire example, input A, input B, output Y. These all are ports, correct? These all are ports. But I told it is a wire data type. But where is the wire data type? Okay, you see the default, it is wire, it is continuous. Okay, so the input port, output port, and we give. Okay, so see, we can assign it directly and you can see that it is correct. Okay, now here you try to understand. Now I am writing a test bench for this wire example. Please try to understand. Okay, for writing this test bench, okay, I want to store A and B data, so I am using the reg data type. If you didn't use the reg data type, wire means I cannot store the data over here. Okay, and then I cannot use it in the initial block. So I want to use somehow the input to use to show you. I want to go and use this data to store the data in it. So that is why this A and B is considered as the reg. Then the output is wire, no problem. Okay, so this will be updated because of the wire. Okay, because we will not use y in the initial begin block, that is the procedural block, and we are using the wire. So that is the thing which you have to understand. Now this is the hardware. Okay, this is the hardware, and now this is the logic. This is the what you would call architecture. Okay, now I want to connect this architecture and test it. So I am creating an instance of that thing. I am creating an device under test, some instance of this wire example. You know it clearly, that's not a big deal. And this is the port, and this is the signal, intermediate signal I am going to create. So I am mapping with the instance signal. How I am mapping the instance with the port? By the name mapping dot A, dot B, dot Y, and I am mapping it here. That's it. Then something I want to use and I want to view the result, I want to store it. So I am using the procedural call, procedure. I am using the procedural block, initial begin, and then I want to go and see the output in the console. So I am going and printing. So whatever, if you use monitor, whatever the changes happening in A, B, that will get monitored and it will be getting printed. So that is the usage of this monitor. And whenever there is a change in AB, there will be a change in output because it is a continuously driven. So these are the things, and I am using the finish to finish it off. Okay, so the command to okay, 1_wire and 1_test bench. Okay, so I'm not creating explicitly an output file. So if we didn't create an output file, it will go and create its own a.out is the output file. Okay, hope you got it. So by using VVP, I am able to get it. So I'm able to see monitor and with finish, and we will try to check without finish. Okay, we will try to check without finish. It is getting, but for some time it will get hanged because it is suppose if you go and implement the RAM and such kind of things, it will get hang. To have that finish statement, to make it complete, we'll go for it. Okay, so somehow our AND gate by using the wire, so already we learned it. Now right now I am talking about the data type. For that purpose I am revisiting this. That's it, no other thing. Okay, so this is one way of the steps. Okay, next, for the reg. Okay, please try to the thing, it looks easy, but to keep it in our mind, it is so. Okay, here we are not mentioning anything, that is okay, no problem. But here explicitly we are mentioning it. I want the output to be of reg type. Output to be of reg type. So when the output port want to be of reg type, I cannot use assign. I cannot use assign. So I want to use always block. So the syntax of always block is always at, and you have to give the inputs. You have to give the inputs and what is the output, those things. But since it is the combinational thing, suppose we forgot the sum, because this is going to be a sensitivity list. If we give star, it will take all, so we don't need to worry about it. And this is the architecture we are building. This is our hardware architecture we are building. We are giving a module, and we are defining our input and output port, and we are ending the module, and this is the architecture we are building it. Okay, so what I am trying to tell is, in an VLSI Verilog design, you have an input and output that is external, and you have a sandbox that is nothing but an internal, that is the architecture. So architecture, first we will go and define our input and output, then we will write our architecture logic over here. Here our architecture logic is AND gate. That is what we went and wrote it. Okay, so this is the model which this is a thing which we want to follow. Then for the test bench, okay, see here, this is different from this AB, and this Y is different from this Y. Please don't get confused. Okay, if you want to change the name, you change the name. Okay, that is not a big deal. Here we are creating a signal. Please try to understand. Here we are creating a signal where we will map it with the port. We will map it with the port. Okay, so that signal can be anything, maybe reg type or wire type. Accordingly, you want to go and use it. Okay, so usually the input we will keep it as a reg type, because we want to store the data and you have to test it. So you need a reg type, and usually our output we will keep it in a wire continuous type, where we will go on to look it. That's the idea behind it. Now I am creating an instance for the reg example, and that is device DUT. You can give the name, any identifier name you can go and give it. And then I am mapping the port of this reg example module with my signal, this one, and the port with the signal, output port with the signal. Okay, so this and this can be different name, no problem. But whatever the thing you are given in the reg, that you have to mention it here, and whatever the thing you are given here, that you have to mention it here. Okay, so this is the idea. Okay, so here we went and created the instances, and we mapped the port. Now, since we are using the reg, and we have to use the initial block. So in the initial block, we try to change its variable, and we try to check whether the hardware is performing correct or not. Okay, so this is the idea behind it. So I verilog, let me use 2 underscore reg, and then 2 underscore test bench. Okay, so now that a dot out is overwritten by this output files. Okay, so now the output will work for this one. Okay, since it's the same thing, no problem. But by using the same wire and reg, we implemented the and you are able to see the difference of the code. That is very much important, you have to understand. So whenever you try to use reg variable, you have to use always block or initial begin to do the things. Okay, And when it comes to the implementation, reg, then this is something you have to go and use for implementing the architecture, always block. And for testing, simulating, go for initial things. Okay, so this is the stuff which you guys want to understand. The next idea, let me go for an vector. Let me go and work for vector. Let us go and work for vector. Okay, okay, I told vector. Okay, I told vector I am not using any design file. I am not creating any hardware design files and all, nothing. Here only simulation part. Please understand. Okay, here only simulation part I am doing it. Here no. See, already the module is vector example. I don't have any input or output port. I am not using it. Okay, and in between I am trying to create a vector of which is having a storing a variable of 8-bit, that is data bus. Just it is nothing. It is only a vector and it is going to simulation type to explain the vector type. Here no architecture, nothing. So you have to understand these type of things also. Okay, so to understand the vector, I created an example, but in verilog it will expect module and end module, all such kind of things. So I went and created a module called vector example without any input port or output port, because I don't want any architecture thing. Just I want to explain what is the vector concept in the iVerilog. So I went and used this 8-bit, and this database, it's an 8-bit, it's a binary. Yesterday I taught you, and that 8-bit is given it over here, and this will display the complete data bus, and this will display only the 0th bit, and this will display only the MSB, this will display the LSB. That's it, nothing. There is no hardware logic, there is nothing. So you have to understand which code is having hardware logic, which code is not having hardware logic. So that kind of discernment you guys should work. You guys should get a thing of it. Okay, so then you can go and do many things. Okay, so now that a dot out is getting overwritten by this output. So now I will get an output for this one. Okay, so this is a complete vector I am able to get. So somewhere in your logic, if you want to go and use the vector, you can use this as an example, and you can go and implement in your hardware logic or some other logic. Okay, so please try to be little bit attentive. Okay, the same thing for the slicing. Okay, what is the meaning of slicing? Vector slice. Okay, I have a 16-bit of vector. I have a 16 bits. Okay, I am making the data as a 16-bit. Then what I am trying to do, I am taking the upper byte and the lower byte. How I can take the upper byte? This is the slicing. From 15 to which location you want, you can slice it, and from which to where you have to slice it, you can slice it. So that is where the slicing operator come. So here nothing logic, just to explain what is in the okay, then that's it. I'm able to select and I'm able to get it. Okay, you might be using these kinds in the for. So likewise, we have concatenation. Yesterday we are talking about concatenation, no? So A and B is having 4 bits, and by using this I can go on concatenate and I can go on do the things. So I verilog, and I'm using the 5th one. Okay, and then when I try to use, I'm able to concatenate 1010 1140. So somehow the 4-bit I can use this concatenate logic for this. Okay, then likewise replica, as I told earlier, 1010 4 times it will go and replicate it. That is not a big deal. Okay, then an example for the integer type. An example for the integer type. See, right now what all I am doing is nothing logic at all. There is no logic at all. You have to understand that concept. Okay, there is no logic at all. Just to explain about the integer, just giving an compiling and giving you an idea. That's it. Okay, so there is no logic. I verilog 7 to explain about the integer, giving it. That's it. The count, it is 25. That is not a big deal. Now, if I want to do some negative integer, how do I do that? Negative, because the same integer, you can work for negative also. Okay, so it will give minus 15. Okay, it will give minus 15. Now, okay, and I can use this integer in the loop also. I told no, I can use this integer in the loop. Okay, for the loop you can go and use like this. And for something, if you have multiple statement, you have to define, you have to start with the begin and end. Okay, begin and end. So that is the syntax for the for loop. And then I verilog, I can use I verilog, and then the loop, and then VVP. Okay, so I'm able to get 0, 1 to display. Okay, so these are the things we will be using in our other sessions. Okay, there you shouldn't get confused. So now this is unsynthesizable. Here no logic, but we are using a real. And if we want to indicate a floating point number or a decimal point number, okay, so you want to go and use such kind of things. Okay, so I'm able to print the decimal numbers also. Then arithmetics. So when it comes to the arithmetic max, I told no, for the simulations you go and use the real voltage current or something like that, and you can go and get the, here we have a some logic, but it is not going to give me an what I will tell a hardware thing or not. Okay, so that there is no input port and output port. I am not mentioning anything over here. Okay, just for the simulation purpose we are using it. Okay, hope. Okay, so I am able to do the arithmetic operations. Now this you have to understand this signed and unsigned stuff. Okay, so reg 78 ff. Okay, what is the decimal value? Let us try to understand what is its decimal value. Okay, so let me go and use its decimal value. I verilog. Okay, I think 12 unsigned, and then VVP out. Okay, so 255. I'm getting 255. The highest number I'm getting the 255. Now, if we go and check for the signed, you see I changed the thing to signed because default reg is unsigned. I'm changing it to signed, and I try to understand what is this data is variable is going to do that. Okay, so you see I'm getting -1, not ff, because all ones in a signed variable of 8-bit, it is -1. Okay, so these things we have to be take care when we try to do the uh, involve in the project. Okay, so now let us see the signed variable with wire. Okay, signed variable with wire. Okay, so we have an, please try to understand, we have a wire signed. Okay, now we went and assigned -5 and +2. Okay, this is how you have to go and implement it. I verilog 14. Okay, I used 13. Huh? 14. Okay, now VVP out. Okay, now you see that the value of -5 is written in the 2's complement. You have to understand that. That is very much important in signed and unsigned. You have to understand. So inside our computer, whichever law is having a signed thing, it is stored in the 2's complement format. And if you want to read it, you have to take 2's complement of this. Okay, when I try to take 2's complement of this, 0 0 1 0 0 0 it becomes, then adding I want to add it with 1. Okay, so 4 plus 1 5, and already this is 1, so 5. So that is the idea behind it. Hope you are able to understand. Okay, and you see that positive is stored in the same. Okay, for the thing, let me put it minus, and this, let me change it, so you guys will be having a better idea about it. You see, it changed. It is stored in the 2's complement, but it is actually stored in the right way. So these are the small concepts which you want to understand it. Okay, now tri-state. This is another another thing which you have to understand. Okay, this is the tri-state just for the demo purpose. Okay, you can give either here wire or try, try. Wire also work for the tri state. Okay, enable data and wire bus, I am assigning it. When enable is 1, data will zone. When enable is 0, z want to be get zone. Okay, now let me run only that. Let me run only that one. Okay, so now I verilog 15 signed VVP. Okay, now we got it as all Z. We got all Z. Data is Z. Okay, all are Z. We didn't, in default form, when I try to give, all the things all are in floating point, are in high impedance state. This is one good example. You see that I didn't map anything. I didn't give any value to enable data and bus. Simply I assigned the logic. You see that. Now when I try to use the test bench, reg enable data, and I try to map it, then when I try to do this kind of all kind of enable 0 and what is happening, you can see the real result. Okay, okay, so when the enable is 0, it will go for Z. When the enable is 1, data is 0, the bus is 0 only it is taking. So something is driving. Because of wire, it is not taking a floating point, something is getting drive. When enable is 1, data is 1, bus is 1. When enable 0, even the data is 1, the data signal is not enabled, so the bus will be of floating point. It is of nothing. Okay, these are the things which you want to understand. What about the test bench code, sir? Test bench code for what? See, for the hardware design, if you want to test, you can test in the design file itself, or else you can keep a separate file and you can keep it as a test bench and you can go and test it. That is the thing. And in order to explain those variables and keywords, I didn't use any design file itself. Directly I went to showing the test bench itself. That is the idea. I hope you got it. So this is one example for the supply. Since I have given you supply is ground 0 and supply 1 in the thing I am trying to give, and then wire Y1 and WR. Okay, so these are some examples. Maybe you can try. Okay, these things you can try. And for the try state, okay, here you can give wire or try, it will work. If you give wire and try, it will behave in the same thing. Okay, so these all are some concepts uh, regarding our data types and some examples regarding our data types. Okay, maybe on tomorrow's class we will try to look into the uh, parameters, memory, array and string. That will be more. Okay, slowly we are trying to build our verilog muscles. Okay, and if you guys have any doubt, please let me know. Meanwhile, let me go and send the PPT. Already it has been sent. Okay, so you will not be having any issues. Okay, okay, hope. Okay, since you guys don't have any questions, we will see tomorrow with parameters, memory, strings, arrays, and tomorrow we have a lot of many examples. Okay, okay, thank you all, bye, see you tomorrow.